Is it visible now?
Yeah, visible, sir. Perfect.
Yeah, fine. Oh, तुम लैब रे अछ तो ओके अछि
Hello.
हेलो
Audible?
Yeah, you
Yeah,
are
yeah.
audible, sir.
Hello.
Hello,
Yes, ma'am.
sir. Good morning,
Good morning, good morning.
sir. Myself Archana Sahu and head of the department here from RPS Degree College, Valana. Here with all our department and around 120 students around here in seminar hall waiting for your talk. Let me introduce first of all our expert sir is Dr. Dillip Kumar Bisoyi, and he is my direct teacher in NIT during my MSc studies, and we along with our faculty members and students, we are fortunate to listen your talk, sir, with a vast experience of 40 years in teaching and research. It will be a wonderful talk. We are waiting for a long time to listen you, sir. And next I welcome our principal, sir, to say something about sir and our department. Over to our principal, sir.
Very good morning to all of you.
Very good morning, good morning.
Good morning, Dr. Dillip Kumarji.
Yeah, good morning, sir.
Sir, you are heartily welcome on a very
Thank you.
that you have accepted our invitation on a very short notice.
Rather, I am very happy to have such kind of talk with the students and my colleagues. I'm very happy, very happy.
Thank you, sir. We are also mentioning here that our students are also eagerly waiting after knowing your experience in the field of physics, and we feel very delighted to be with you. And after discussion on the topic of X-ray optics for material characterization, it is where the physics theoretically, but it also becomes most important to know the basic meaning of physics experimentally. In a very simple statement, you can say X-rays plays a vital role for the characterization of materials. And we are very lucky that Dr. Dillip Kumar Bisoyi is along with us, and we will be very you can say cherish the interaction with Dr. Shah and understand the logic of X-ray, in what way makes the characterization understandable, and application of every material is directly linked with the characterization. So I hope so this interaction will be very fruitful for all of us. And again, I must congratulate to Dr. Sir Bisoyi that they have accepted our invitation on a very short notice. And thank you very much, sir.
Okay, thank you very much, sir. So let me start then.
Yeah, you are most welcome, sir. Please start.
First of all, I must thank Dr. Singh, Principal, RPS Degree College, Balana, Mahendra
Mahendragarh.
Mahendragarh, to allow me to interact with you, students and faculties, my friends. Some of my friends have also joined, even from the globe, not from India, outside India.
Very
Uh,
nice.
and then next is my direct student, Archana. I taught her in 2001 with a little bit of X-ray, of course, not in detail, in solid state physics. And he passed from this department in 2002. At that time, it was not NIT, named as REC-Rourkela,
Yeah,
Regional Engineering College, Rourkela. Yeah, even my time also. I am also a direct student of the same department, both MSc as well as PhD. MSc in the year 1984, PhD in the year 1991. And then I must thank all my colleagues, students, friends who are encouraging me always to go for such kind of talks at school, college, university, institute level, and to um, make our students or make the future of the nation active and play their role so that our nation can be developed. Then last but not the least, there, thanks to my mentors who make me to uh, able or capable of interacting with students all the time, starting from school level till PhD level. I am very much interested to discuss, interact with school level students also. I haven't interacted starting from 5th standard, 4th standard students till PhD level students. Rather, I am very, very happy always with interaction with the students. And first of all, I should thank all those who are involved in these activities. Then let me first start with some introduction before going to the slides. Let me tell first, what is science education? Science education must be reflected not by the marks or grades in the examination, but by understanding the nature and natural phenomena in the language of physics, chemistry, life science, engineering science, medical science, earth science, many science, etc. And another thing, there is a very important law, rather it is called as the natural law, which controls everything in this nature, that tells every system always tries to become stable. Every system always tries to become stable by possessing minimum energy. It is applicable for all the branches of science, physics, chemistry, life science, engineering science, medical science, earth science, any science. It is a natural law. It controls the whole nature. It doesn't matter whether it is physics, chemistry, life science, engineering science, medical science, earth science, any science. So it is a law called as law of nature. I don't know whether people or the students might have gone through it or not, but it is a general law controlling all science branches. All science must be expressed in that law. If one can able to understand the phenomena in nature with the help of this law, then he understood everything about the nature. That is the importance of that law. So then now let me start with the slides. The topic of this today's presentation is X-ray optics for material characterization. So I will begin with the reverse direction. First, let me know what is characterization, then material, then optics, then X-ray. So all of us might have heard about the word character. Even with us, we have some character. Every person, may it be big or small, whatever it may be, every person has a character. And this character is associated with the all behavior, quality, whatever you may think. But the character is associated not from appearing the face or laughing, crying, but rather it is directly relevant to at the genetic level. At the genetic level. So if you want to understand the character of any people, then one must have to understand the gene behind it. It is coming from the genetics level. So like that, suppose think about a material. I am telling material in the sense it may be living or non-living, broadly classified into two categories: living material, non-living material. We are all living materials. Then the other materials which are available in nature are not living or non-living, like all plant kingdom, animal kingdom, they are all living materials. And similarly, there are many more natural materials which are also non-living. I refer to only nature, but you can think in the other way also. The material may be living or non-living, because some of the materials which are non-living, which are synthesized, which are fabricated by us for our benefit. But nature is nature. It has both natural living material, natural non-living material. How think about a stone, which is a non-living material of nature, that we got it from the nature. So then now that is about the material. Then next is the optics. Optics is a very common branch of science, engineering, medical science, all the branches of science, because we are collecting information with the help of that branch by interacting the light energy with the matter. After interaction of light energy with the matter, various phenomena are occurring. May it be reflection, refraction, transmission, polarization, absorption, interference, diffraction, many. But ultimately, we are collecting the information of that system with the help of light energy. So all relevant phenomena, when the light energy is interacting with the system, is coming under that branch we call it optics. And then if you go over the electromagnetic spectra, then there is a region where there is a region in the electromagnetic spectra where this X-ray is falling. It is within the wavelength range of 1 to 100 angstrom in the electromagnetic spectra, and all electromagnetic spectra are the light. Light means it never be mean that it is only visible light. Whole electromagnetic spectra itself is light. And when we are telling optics, all the relevant laws that are framed in optics are never applicable only for the visible light, rather it is applicable for the whole electromagnetic spectra. So then now, yes, then let me start with my department with brief history. The PhD degrees are awarded in the field of small angle X scattering from the Department of Physics and Astronomy, REC, now it is NIT-Rourkela. And the history tells that Professor T. Ratho did his PhD in Austria under Graz University with Professor Kratky, who is the man behind that field, that is small angle X scattering. He designed a camera there, which is called the Kratky camera. So after completing the PhD, then Professor Ratho tell to Professor Kratky that, sir, I have learned lot many things in my PhD work, but what will I do when I will come back to India? Then immediately Professor Kratky told him, will you please go with the camera which is here in my lab. Then with that camera, he came back to our institute, that is REC Rourkela at that time in 61. Then he started research work in the same field, that is small angle X scattering. And there are few list of candidates awarded PhD degree. The first one is Dr. P.C. Panda in the year 1969. So already 50 years passed of that field of research work in our department in NIT-Rourkela. And Professor Dr. P. Panda has retired as the director, Indian Council of Agricultural Research, Pusa, Delhi. He is still alive, but the rest, next is the Professor N.C. Sahu, who was the head of the department here, and my supervisor, Professor T. Misra. Then Dr. A. Patel is not here, he is in US now, but got the PhD from our department in 1977, like S.N. Tarasya was the director, planetarium of our government of Odisha. Then next, K.C. Patra was the faculty member here. Then this is a long list, and my name is probably in 8. I hope so, yes, 8. I did my PhD in 1991 from this department after completing my MSc in 1984 with X-ray specialization. Because at that time there are two specializations, one is X-ray and the other one is electronics. And I have X-ray specialization. And various samples or various systems natural, artificial, were analyzed with the help of this technique, which is called as the small angle X-ray scattering. And then now, next we'll come for the topic. I told you about the materials and characterization part. Then first important part is the optics. So what that optics means? Optics, it is broadly classified. It is a branch of physics, no doubt, under which you will study the interaction of light energy with matter and relevant phenomena that happen there. Because when light is interacting with the matter, various phenomena may come over at a time, may it be reflection, refraction, polarization, interference, diffraction, scattering, many. And that too again, they are not coming one after another, rather it is coming at a time, provided if the condition for those phenomena are satisfied. So in that way, the branches of physics are like this. It is the behavior of light, then the interaction of the objects, and the instrumentation. It basically covers the whole branch of optics. What is the behavior of light? How it is interacting with the objects? And then what are the instruments that is used in that branch of optics? So broadly, it is classified again into two parts. One is the geometrical optics, other one is the physical optics. And what it means that geometrical optics is also sometimes called the ray optics, that follows the reflection, refraction phenomena in the form of ray. Then next is the physical optics, and it deals with the wave character, where all scattering, diffraction, interference, all those polarization, all those phenomena are coming there, where we have to accept that it is the wave character of light energy. Then ray optics, the direction of the light along which light energy travels in the medium, that is a ray. Ray is ultimately comes from a wave or wavefront. Suppose you take a spherical wavefront with reference to a point source. At any point on the wavefront, if you draw a tangent and then draw a perpendicular at that point, and that will provide you the direction in which the light energy is going, and that is the ray. So that is the direction along which the light energy is going at that point of the wavefront. Then this is a diagram. All of you might have seen it. There is a incident ray, normal, reflected ray, and there is a surface or interface from which the light ray reflects back. And there is a normal angle of incidence is here theta, reflection is also theta, and this should be same as per the laws of reflection. And it followed by the ray phenomena or ray optics. So this is a beam, parallel beam, diverging beam, converging beam, all those things all of you might have know. Then I told you, when we are telling optics, the whole electromagnetic spectrum is optics, everything, because that kind of radiation has a special character which is different from other kinds of waves, because it is no doubt an electromagnetic wave. The whole electromagnetic spectrum is nothing but the electromagnetic wave or the radiation in which the electric field and magnetic field are vibrating in a direction perpendicular to each other, and again the wave is propagated in a direction perpendicular to both of them, electric field and magnetic field. And the most important character associated with the electromagnetic wave or radiation is that they can travel in vacuum without any medium. But when you talk about the progressive wave, it requires all the time a medium. For example, if you think about the water wave that is created on a water surface, that is a transverse wave, of course, then it takes the energy from that point of disturbance toward the bank or the shore of the river or the pond, whatever it may be. And that carries the energy from one part of the pond to another part. And that kind of wave that is created is progressive because water is the medium there, which takes the energy from one point to another point. And in a similar way, if you think about the sound wave, and then the sound wave, suppose I am sounding here, and the wave is propagating in air medium or some other medium, and it is an example of longitudinal wave, and it goes with compressions and rarefactions. But ultimately, that requires a medium. Who will compress and who will expand unless there is a medium? So progressive wave may be transverse, may it be longitudinal, all the time it requires a medium. But that electromagnetic wave, electromagnetic radiation is such a nice wave, such an important wave. All of us who are taking advantage of that kind of wave every day, every second, is that it can travel in vacuum. And look, the spectra. The electromagnetic spectrum is consisting of all those kinds of radiations like gamma rays, then X-rays, ultraviolet, visible, infrared, microwave, radio wave, and many, many. And they are classified on the basis of their wavelength or frequency, whatever it may be, because you know the relation that the wavelength is equal to the velocity of the light wave or the electromagnetic radiation divided by its frequency. Once you know the frequency, you can get the wavelength, or if you know the wavelength also, you can get the frequency. But what happens when we try to collect the information of the objects before us? It may go to any level in the sense length order. At what length order you want to collect the information from the object or the material? The material may again be living or non-living, doesn't matter. But the order length is important. The most important part is that how to collect the information of that order length with the help of these electromagnetic spectra. May it be visible, X-ray, gamma ray, ultraviolet, infrared, microwave, radio wave. All these radiations, all these electromagnetic waves are helping us in one or the other way to collect informations which makes our life comfortable, easy. So in that way, it is also shown at below at what level, which kind of radiations are being used, because their order length is compatible with the object order length to collect that kind of information. May it be atomic, molecule, then protozoas, pinpoint, honeybee, humans, buildings. All order lengths are available to us, and with the help of this electromagnetic spectra, we are collecting the informations. And the wavelength is going towards shorter towards left and longer towards the right. So that means gamma ray is having least wavelength, here it is shown, and the radio wave is having the highest or longest wavelength, that is shown in the electromagnetic spectrum. Then these are the properties associated with in general electromagnetic wave, particularly visible light wave. So light is an light. When I tell light, light means whole electromagnetic spectrum. Everything is light. That's why optics covers the whole electromagnetic spectrum. Light is an electromagnetic wave that I told what kind of wave it is. The light travels in straight line. Speed of light as it travels through air or space is much faster than that of sound. Velocity of light in vacuum is 3 × 10⁸ meters per second. Then obviously it follows the laws of reflection that all of you might have known. The angle of reflection is equal to the angle of incidence, and the other law tells the incident ray and the normal at the point of incidence, the reflected ray, they all lie in one plane. Similarly, the law of refraction that obeys the laws of refraction also, that tells sine of the angle of incidence, ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant, and that is the refractive index of the second media with respect to the first media. Like that, these are a few laws or few properties of the light wave or the electromagnetic radiation. Then next we will come directly to X-ray. That is our interest, and what that X-ray is. No doubt it is a part of the light or the whole electromagnetic spectrum. And then now we will go little bit details about that X-ray part. So here is the brief history. Ranjan in the year 1895 discovered a ray which suddenly, accidentally in his laboratory when he is doing some experiment with vacuum tube, some radiations are coming out and exposing the film put under the drawer of his table. Then he searched behind the reason why that the film is exposed. And ultimately he got that some radiation is coming and exposing my film inside the desk, inside the table, desk drawer of the table. And at that time, the behavior, character, and properties of the X-ray was unknown. So that he named that ray as X-ray. X always stands as unknown. So in that way, he named that ray at that time as X-ray. But now it is well known, but still the name is existing. It is still the name is existing. And these are a few experiments he did with his wife's ring in his hand. He take the photograph, radiograph, and then a few contributions of him relevant to the discovery of X-ray comes into picture. Then these are few properties associated with the X-ray. Generally, they have shorter wavelength in the electromagnetic radiation. Generally, it is in between 1 to 100 angstrom or 0.1 to 10 nanometer. 1 nanometer is equal to 10 angstrom. So that requires, of course, high voltage. That is the most important requirement to get X-ray. All the time it requires high voltage, and they are used in taking the photographs which are not visible to us with the naked eye, because those X-ray radiations cannot be detectable by the eye, because they are so having so small wavelength. Our eye has the capacity to detect the radiation in the wavelength range which you call the visible. Visible means all 7 colors, starting from near about 400 nanometer to 700 nanometer, all colors coming under that. So our eye is a God-given detector which can detect only that particular range. If any phenomena, anything happens within that range, that length order, then the information can be go to your brain and we understand what is there before us. So the information that we are collecting with the help of visible radiation, that is the all colors, are coming in that way only. But I can never be the detector for X-ray, because X-ray is so small or short wavelength, our eye don't have that capacity to detect them. So we can never collect the information with the help of X-ray, and eye is the detector. So then now it also follows the same laws of optics, same thing, because it is also light, it is also optics, and they are capable to travel in vacuum because they are electromagnetic radiation. That character is the important character which is not there in the progressive wave. Progressive wave all the time requires a medium, but this wave or any electromagnetic wave like X-ray can travel in vacuum. This is a generator from where the X-rays are generated, may it be medical X-ray, may it be laboratory X-ray, may it be synchrotron radiation, but the principle behind production of X-ray is all the same. The basic principle tells that whenever an energetic electron is striking to a target, but the target must have certain properties. Every material can never be a target for X-ray production. If the target is there, then energetic electron when bombarded with the target, radiations are coming out, and that goes to that range which you call as the X-ray radiation. That is a basic principle how X-ray is produced. Then little bit about the origin. Origin means at atomic level how X-ray is coming out. Let us think about a target, and the target must have certain properties like they must have high atomic weight, high melting point, high thermal conductivity. These are must. Otherwise, it can never be used as a target material for X-ray production. High atomic weight, otherwise the transition of electron from one to another orbit is not enough to go to X-ray range. That's why it requires an atom of high atomic weight. Then good thermal conductivity, because unless the target material is having good thermal conductivity, because most of the energy when the energetic electron going and bombarding with the target, 95% of the energy is converted to heat energy. So unless that heat energy is dissipated by some way or the other, the target will melt. And once the target will melt, there is no further production of X-ray. That's why it requires the target must be having a good thermal conductor. Then high atomic weight, good thermal conductor, and another property is also there that is called as the high atomic weight, good thermal conductor, because of the dissipation of the heat energy that is generated by bombarding the energetic electron with the target. And these are the requirements in order to select a material to be a target material for production of X-ray. But when you think about that kind of target means the material from where the X-ray can come out. But then we have to think over the origin, from where actually the X-ray is coming out. Then we have to go back to the atoms, because every element, like for example, the properties, the requirements of the target material for X-ray production is requiring some material. All materials cannot be, like for example, copper is having those properties, so copper can be a target material, molybdenum can be a target material, tungsten can be a target material, but not so many metals are there which cannot be accepted to be the target material for X-ray production, because those properties are not there with those metals. So now you take about an atom of that target. Suppose for example, think about a copper target. So when you are thinking about copper target, obviously it is consisting of copper atoms only. So in that way, you see here is the atom So when the energetic electrons are coming and interacting with the atom, target means atom, it is going to the atomic level. That's why it is origin. From which level? From atomic level actually it comes. That's why that is the origin. So when you think about the origin, then fast moving electrons or the energetic electrons are coming and interacting with the atom of the target. So when it is interacting, what will happen? The electron will get decelerated and change its path as shown in the diagram here. And what will happen when it enters to the cloud of the electrons? Then they will be decelerated. They will be repelled by the field of this electron cloud. And when it is repelled, then they will be decelerated. Decelerated means the velocity goes on reducing. But when the velocity is reducing, kinetic energy is lost, and that kinetic energy rather converted to the X-rays, and hence the continuous X-rays are produced. Continuous means all kinds of waves are associated. That's why it is called as continuous X-ray, because continuously the energy is going out. Hence, the photons or the energy that is coming out in this process is changing its wavelength continuously. That's why this kind of spectra comes out of the atom is called as continuous X-ray. And the other one is called as characteristic X-ray. What that characteristic X-ray means? Suppose one electron in the innermost orbit of the atom is knocked out by the energy of the bombarded electron. Then if the energy is sufficient enough to knock out that electron from the innermost part, then that there is a vacancy. So to fill that vacancy, because now when the electron is going out of the atom, then ultimately the atom will become unstable. And that follows the same law of nature that I told at the beginning. Every system always tries to become stable by possessing minimum energy. So when the electron was there, it was stable. But when the electron was knocked out of the atom, now it will become unstable. So obviously it will try to become stable by taking or by taking some electron to fill that gap. Always it will try. So to fill that gap when the electrons are coming from the higher orbits, then there is a difference of energy that comes out. And when it comes out, it is coming out in the form of X-rays. So, but why it is called as characteristic? Because it will characterize from which target it is coming. If it is copper, then the electron transition from higher to lower orbit may be from L to K or from M to K, whatever it may be. Due to transition, the definite amount of energy is associated if you know about the target. If it is copper, definite. If it is molybdenum, again definite. If it is tungsten, again definite. That's why when you know the kind of radiation that comes out of the target, then you can tell what is the target, whether it is copper, molybdenum, or tungsten, etc. That's why it is called as characteristic spectra. So when X-ray is coming out of the target, out of the machine, then it must consisting of both at a time, or it means continuous as well as characteristic. So accordingly, this diagram is shown here. You can see it is the characteristic, continuous, both are there here, and here you can see. Here you see there. So these two peaks, K beta, K alpha, corresponds to characteristic, and the rest part are all continuous, right? It is for molybdenum, and the voltage applied for that target for production of X-ray there is 35 kV. Voltage is very high, kilovolt. So unless you go to that voltage, X-ray cannot be produced. But when the X-ray is coming out of that arrangement, you can tell the X-ray unit, then it must consisting of both characteristic as well as continuous. And the peak shown here as K alpha, K beta is due to transition, due to this characteristic spectra, the transition. And that is corresponding to this K alpha, K beta peaks. But the rest part, whatever is shown here, it is continuously changing the wavelength. Here is the wavelength, this is the relative intensity. Then you can see how it changes, the intensity changes with the wavelength. And that's why it is called as the origin. So when you think about the origin, it must relevant to the atom of the target. But whenever there is interaction of energetic electrons with the target, ultimately it is associated with both the kinds of spectra, continuous and characteristic. But when you go for characterizing any material with the help of X-ray, we cannot take all the wavelengths because you require a monochromatic source. Monochromatic means single wavelength. So out of many, you have to select which one is helpful to characterize the material at a particular order length. So accordingly, you have to select or filter out all rest wavelengths except that one to be monochromatic. In that way, we have to proceed for further interaction of X-ray with material for characterization. Then application part. You see, this diagram shows many things. There is an organism, right? Tissues are there in heart. Cells are everywhere there with the living being. Organocells are also there. Complexes, proteins, many very complex structures are associated with living, and it is not only with living but also with non-living. The order length is very important. You see, in computerized tomography, CT scanning that you tell, computerized tomography, the order length requirement is 1 to 2 millimeter. You need that order length. Similarly, fluorescence microscopy, it is 250 nanometer. Cryosoft X-ray tomography, 25 nanometer. Cell electron tomography, 5 nanometer. Single particle electron microscopy is 0.2 nanometer, but X-ray crystallography is less than 0.1 nanometer, means less than 10 angstrom. And the resolutions are mentioned here in millimeter. That's why it is coming from left towards right. You see the order length, how important it is, and how to select your radiation to go with different kinds of experiments, whether it may be relevant to spectroscopy, maybe absorption, maybe scattering, maybe diffraction. Most important part is to collect the information, but at what order length you want the information, whether it is in the nanometer, millimeter, kilometer, whatever it may be. But accordingly, you have to select a particular wavelength of the electromagnetic radiation for the interaction to go for different kind of phenomena, may it be reflection, refraction, transmission, polarization, absorption, scattering, diffraction, etc., etc. So after that phenomena only you are able to collect the information about that material, which you call as the characterization. Then if you go for the spectroscopic characterization with the help of X-ray, it is called the X-ray spectroscopic characterization. Then obviously once you are telling spectroscopy, like for example, as is shown in the origin of the X-ray spectra, once you are telling it is spectra, it is a graph between wavelength or frequency, because you know the relation between wavelength and frequency, and ultimately the ordinate must be the intensity. How the intensity varies with the wavelength or frequency. Because if you consider the wavelength, obviously, if you consider the whole electromagnetic spectra, you can never place them in a paper. Rather, it will cover the whole room to represent in terms of wavelength. So it is better to represent them by frequency. So usually it is expressed in terms of frequency. Frequency means wavelength inverse. The order length will be wavelength inverse, so that you can represent the spectra in a very limited zone, region, even on your paper. So when you're telling X-ray spectra, spectra means the kind of energy that is coming out with the help of X-ray. And if you know the energy of that X-ray that comes after interaction with the material, may go with different phenomena like absorption, scattering, fluorescence, diffraction of this electromagnetic radiation. Knowing those radiation energy, you can tell what kind of material it is. That is X-ray spectroscopic characterization. And they are defined as the short wavelength electromagnetic radiation produced by decelerating the electric energy. So when it goes on like that, then X-rays are coming out, and that X-ray will tell you which kind of material is giving that X-ray, and that is a characterization part. So electronic transition of electron in inner orbital of the atoms, that is also another kind of transition, and which tell when the X-ray is coming out. So in that way, this is a device. You see, here is a sample. Electron beam is bombarded, then X-ray is ejected out, shown as the wave nature. Then it is detected by the detector. Then again, because the signal is very weak, rather to amplify it, there is an amplifier circuit, and that amplifier circuit is communicating the message to computer, and that is the data output. That is a display. It will display the spectra, and this is shown as display. In that way, it is doing the experimentation to collect information about the sample or the material. This is you see how complicated the instrument is. So then next is the principle of X-ray fluorescence, because X-ray fluorescence basically tells fluorescence is a phenomena. You know, X-ray is an invisible light. Visible and invisible are not that the radiation which is visible called as the visible radiation, which is not visible as an whole electromagnetic spectra. No radiation is never visible. No radiation is never visible. But when you are telling visible spectra, it means this visible spectra or this region of the electromagnetic spectra is helping us to visualize the objects, because eye is the detector. That's why. And that is the reason why you are selecting that range as the visible spectra. But whereas if you go to the either side, ultraviolet or infrared side, they are not detected by eye, or any God-given detector like skin, ear, tongue, everything. There are 5 God-given detectors, including eye, and no one can be able to detect those invisible radiations. That's why they are called as invisible. Invisible means not relevant to thing that the eye cannot visualize. Visualization is different thing, and here it is visible. Invisible is defined in terms of whether that kind of radiation is helping us to visualizing the object before us or not. In that way, the visible spectra is helping us every second to collect information about the object before us. That's why it is visible. Rather, when the X-rays or the gamma rays, microwave, radio wave, they are all invisible, but they are helping in one way or the other to collect the information also, and we are doing so every day. So every electromagnetic radiation is helping us in one way or the other, may it be visible or invisible. So the principle of X-ray fluorescence tells, so yes, now what is the fluorescence? Fluorescence means that X-ray photon, X-ray is invisible radiation that I told. When it is invisible, it is very difficult to detect. So what will happen? Taking that visible photon energy, if it is bombarded with some kind of element, then that interaction will produce some photon which is visible. So that is called as fluorescence. It will give you visible light. In that way, it is called as X-ray fluorescence spectroscopy, XRF. And that helps to characterize the materials also, because it will tell you when fluorescence comes out, it will tell you from where it comes out. And once you know that, then it is characterized what kind of elements are present in that material. So that way, the elements are the, for example, steel plant is producing steel, and steel's main component is carbon. The strength property of the steel is depending on the percentage of carbon present there. So all the time, every time when the production or the materials are coming out of the plant, they will go for that kind of test, that is XRF, to know whether all the relevant elements are in proper ratio to have the requisite property for the steel or not. If it is yes, then it will be marketed, otherwise it will be rejected there itself. And they will think about the production part, how it can be achieving the best quality so that it can be marketable. Because unless the quality of the material that comes from any industry is having requisite properties, it is very difficult for marketing, and after a few days or years, obviously the industry will be a sick industry. So for characterization part of any industry is therefore having a quality control unit, every industry, and it should be. And if it is not there, quality can never be controlled. What kind of quality that material is coming out of the industry can never be controlled. So the quality control cell or the unit of any industry is having such kind of device that is called as XRF, X-ray fluorescence, to detect what kind of elements are present inside the material produced by the industry. And similarly, another is particle-induced X-ray emission, PIXI. It is a very well-known technique in the sense that there are many archaeological materials, like for example, Assoc stamp. People could not understand what kind of elements are present there inside it, so that it is not rusting. If you take an iron or any material, then generally it is corroding. But what kind of material, it is prepared so long back, but still it is not corroding. That's why if you go for such kind of archaeological material, you cannot break it, because once you break it, everything is gone. So without breaking, if you want to analyze the structure, analyze the elements present in the system, that can be done with the help of that technique, which is called as the particle-induced X-ray emission. And knowing the X-ray emission, you can detect what kind of elements are there inside that material. And generally, it is used for archaeological characterizing materials, archaeological materials which are requiring characterization. And this is another very important spectroscopic technique that is called as X-ray photoelectron spectroscopy. What happens here? The X-ray is focused to the surface of the sample on the buffer, silica buffer. Then the electrons are ejected out, and electron collection lens is shown in the diagram here. And then that gives processes, and ultimately it gives the graph or the image as shown in the wafers. On the silicon wafer, then you see the spectra is shown here, and that spectra will tell what kind of binding energy are associated with the electrons present inside the material, so that you can understand in depth how that material the elemental interaction is there within the material. That characteristic technique is called as X-ray photoelectron spectroscopy. Similarly, the other characterizing techniques are absorption, which is very important, that is used in the medical also. When we are taking the advantage of medical application of X-ray, basically it is done in two ways. One is called as the radiography and other one is called as the radiotherapy. And the absorption process, all of you understand, it is explained in the slide mathematically also. What do you mean by absorption and how absorption happens and how it is helping us to give the information with the help of that kind of absorption technique. And in medical, it helps in two ways. One is called as the radiography, another is called as the radiotherapy. Radiography, all of us might have understood, because when there is a fracture of bone somewhere, or there is a foreign element present inside the body. For example, there is a bullet inside. Unless the doctor will locate where the bullet is, how can he operate it out? So to locate the bullet where it is, because bullets are very much dangerous in the sense that it is made up of lead, and lead is poisonous. If it will remain there inside our body for a longer time, it may happen that it damages the body components. Ultimately, it may lead to death also. And that's why how to detect where the bullet is inside the body. So to do that, whether there is a fracture in the bone, whether there is a tumor cell in the body, whether there is a bullet inside the body, unwanted objects are coming inside the body, we have to scan the body to see where that kind of defects are present, or the bullets are present, or the tumor cells are present, so that doctor or the physician will take action accordingly. Otherwise, it is very much difficult to know where the bullet is, where the defect is, where the fracture is. All those things are very top job. So that's why we are taking a photograph with the help of X-ray radiation, and that photograph is called as radiography. And knowing the radiography, understanding the radiography, doctor or the physicians, even we can understand where the fracture is in the bone, where the bullet is inside the body, where the tumor cell is inside the body, all kind of information which we can never collect with the help of this visible light and eye as the detector. But with the help of X-ray and X-ray film as the detector, we can collect the information that where is the fracture and where is the tumor cell, where is the bullet inside the body. Foreign elements are present sometimes, that creates problem. So in order to understand those things, we're all the time going for X-ray radiography. And similarly, the other one is called as the radiotherapy. Therapy means generally there are various kinds of therapy like chemotherapy, physiotherapy. Physiotherapy means with the help of physical phenomena, we are controlling the body activities. Like for example, exercise is a physiotherapy treatment. And whenever you are going to medical, they are going for that kind of treatment, physiotherapy. Doctors are advising to go for that kind of physio exercise so that it can be cured. And similarly, when you are telling the radiotherapy means there the radiations are used. That's why it is called as radiotherapy. And generally what happens, if there is a tumor cell inside the body, there is all the time possibility that if it will remain for a longer time, it may lead to cancer. So if you detect that tumor cell where it is and kill it, then there is no chance of going for that kind of disease, which is cancer, right? So then, but to kill that tumor cell, first of all, where the tumor cell is, how much it is growing, how much mass it has, depending on that, the physician will have to decide how much energy of the radiation will kill that cell. So knowing the dose, then they will irradiate the tumor cell with the help of these X-ray photons also, because they are very much energetic photons. So when they will point it out to that particular tumor cell, ultimately the tumor cell will die and there is no further chance of going to cancer. In that way, the therapy is called as radiotherapy. Not only X-ray radiation, sometimes gamma ray radiations are also used, depending on the dose. How much dose is required to kill that tumor cell? And that is called as the radiotherapy. So one is radiography, to take the photograph with the help of X-ray light or X-ray optics, and then find out where the bullet is, where the fracture is, where the tumor cell is. All those things are done with the help of radiography. And the other part is the radiotherapy, to kill those kind of unwanted cells, which are tumor cells. That is called as radiotherapy. Then next is you see, these are the medical imaging part that I told already, how it is helpful. Now, but another advantage with we people, because of advancement in the technology, we are now able to go for the digital photographs of radiographs. Earlier, what happens? They have to take a film, then they will go to the dark room, then they develop the film, then finally they have to check, and it will take long time. At least minimum it requires 4-5 hours. But with the help of digital X-ray radiography, within 5-10 minutes you can know everything. That is technology doing that. And similarly, this computerized tomography I told, that is CT scanning. What happens? The difference between these two is that when you go for radiography, it will scan the whole body. But think about a very complicated system like our brain. If there is somewhere some clotting is there inside the brain, then it may go for paralyzing the body. So unless you locate where that clotting is there in the brain, it is very difficult to go for any kind of surgery or remedies. So then now how to locate the clotting? When you go for such kind of clotting, then they are taking the help of the technique which is called the computerized tomographic scan. What this means, they will divide the whole brain, the three-dimensional brain, into just like slices of the bread. So every slice will tell you where that type of clotting is there. That is the basic principle of computerized tomography. It will scan just like the slices of the bread, so that the whole picture of the brain that comes in radiography is not enough to give that kind of information if there is such kind of clotting in the brains or some important organs like heart, kidney, anywhere. So in order to identify exact location of that kind of clotting or that kind of defect which may harm our body, can be done or can be scanned with the help of that kind of, then they will take the help of computers, and that's why it is called as computerized tomography. They will take them as a slice and then they combine them for getting the whole structure. That is called as computerized tomography scan. So these are the few pictures relevant to medical X-rays. X-ray machine is there. Then scan the body for different organs to locate defects, bullets, fractures, etc. There is CT scanning. Then next will come for the scattering and diffraction phenomena. So now the very important phenomena, if you go back to the history of science, till now, whatever informations we are collecting at the atomic, ionic, molecular level, it is because of these two phenomena, scattering and diffraction. Although many phenomena are there, many phenomena we learned, like reflection, refraction, polarization, interference, many absorption. But the most important phenomena that helps human being to collect information about any material at atomic level or molecular level or ionic level is only two, that is scattering and diffraction. So what this phenomena basically tells, all of you might have know about the diffraction with a grating, the students grating that you might have done in the laboratory. And basically, what is the purpose of doing that experiment? How it helps to collect information about the object that is the grating. Let me tell you first, suppose for example, a grating is given to you, because grating is nothing but a glass plate over which the lines are drawn to create opaque lines. Those opaque lines will not allow the light to pass through it. So in between two lines, you will get a slit. So there are many parallel slits there in the grating, right? So then that parallel slit, when parallel slits are put together with the help of a light source, it will go for diffraction. And diffraction is a phenomena which is nothing but the phase relationship among the scattered radiations that comes from the object when light interacts with that. So when light, but again the order length is coming into picture. Order length, when you think about a diffraction experiment, the order length is very important. The order length tells if wavelength of the radiation, that is X-ray, is comparable to the dimension of the object about which you want to collect the information. If they are of same order length, then it will go for diffraction. But if the wavelength of the radiation is extremely small, wavelength is extremely large in comparison to the object with about which you want to collect the information, then it is the example of scattering. So the order length will decide whether it is a scattering experiment or it is a diffraction with the help of X-ray. If it is X-ray scattering, obviously the X-ray is taken. Similarly, X-ray diffraction. But generally, scattering and diffractions can be done with the help of whole electromagnetic spectrum, and with the help of these two phenomena, scattering and diffraction, lot many informations were collected. Rather, for example, size of the nucleus, size of the atom, size of the electron, size of the proton, many. All those informations are collected with the help of these two phenomena, scattering and diffraction, using suitable radiations to collect the information. That's why they are very important phenomena, that is scattering and diffraction. But again, when you are designing or thinking about to design an experiment with scattering or diffraction, the order length matters. You want to collect the information at what order length, and accordingly you have to select your wavelength of the radiation. And similarly for X-ray. X-ray is having also a wide range of wavelengths. Which radiation will be helpful to collect the information with that order length present inside the material? That will tell you you are going for diffraction or scattering, and that will help us to collect the information about that material, which you call as characterization, to understand the structure. And those informations can be collected with the help of this scattering and diffraction, and particularly with the help of X-ray, if then it is called as X-ray scattering or X-ray diffraction. You see, these are the phenomena that may happen when the radiation or the light or the optics you are dealing with. Reflection, absorption, refraction, scatter, light diffraction, like that, all those phenomena that we are visualizing in our everyday life, right? Because light radiations are all the time there with us, may it be visible or invisible. Even in the night when we are sleeping, you cannot tell that we are not interacted by the radiations, because gamma radiation, X radiation are everywhere there. Nobody can check them. It can come through the walls, come through the doors, it can come and all the time interacting with our body. So even in darkness also, you can never tell that we are not interacted by any kind of radiation. It may not be visible radiation, but must be with some of the electromagnetic radiation. All the time comes and interact with us. So then how to protect our body from them? You have to take measures to wear the dress material, sometimes to wear some metals, something else, only to protect us. But we can never say that our body is never interacted by any kind of radiation during night when we are sleeping. So the various phenomena that happens with the help of radiations interaction with the matter goes like this: reflection, diffraction, absorption, scattering, polarization, diffraction, interference, many are there, which all the time going on around us in this nature. And this is a few points to be distinguishing scattering phenomena with the diffraction phenomena. So the phenomena is observed both waves and particles. Scattering is a property of the wave interaction. Some phenomena are some forms of scattering, like Compton scattering, basically, where it is an inelastic scattering, because when the energy of the photon is interacting with the electron, after interaction with the electron, there will be recoiling of electron. Electron goes with some velocity, but it is and again the same photon will go with some other velocity. So some of the energy is being taken by the electron, which is the recoiling electron, that takes some energy, and rest part of energy is coming out as the photon. So the photon energy definitely loses energy when interacts with the electron. So when it interacts with the electron, due to that energy loss, what will happen? The wavelength gets changed, because when the energy is lost, frequency is reduced, and when the frequency is reduced, the wavelength is enhanced, right? Because frequency is inverse proportional to wavelength. So in that way, the wavelength or the energy is changed. That's why that kind of scattering is called as inelastic scattering. Thomson scattering is an example of elastic scattering, when the energy is conserved. And similarly, diffraction is the phenomena which also helps us many a times to collect information at a particular order length, choosing suitable radiation to design that experiment of diffraction. It may be X-ray diffraction, it may be gamma ray diffraction, it may be neutron diffraction, it may be electron diffraction, many kinds of diffraction that you might have learned. But all are diffraction. And just I'm telling the difference between the scattering and diffraction with respect to the atom. Let us think about a X-ray photon having wavelength 1.54 angstrom. Because once it is photon, energy packet, you can take that as a wave also. That is, all the time wave particle duality is associated with optics. When you are dealing with light, never think that it is only particle or only wave. The duality is every time there, because some of the phenomena are could not be explained by wave nature, but could be explained by particle nature. For example, if you go for the particle nature of the light, that is the example photoelectric emission. The phenomena of photoelectric emission tell light comes, interact with the metal, and the electrons are ejected out, but not with any kind of radiation that must having energetic radiation like X-ray, gamma ray, energetic radiations only. So then now what happened? If you think that the light is coming and interacting with the metal, because when you are telling the wave concept itself is telling that the energy is diverged from, let us think about a point source. You are getting the spherical wavefronts. How the energy is going out of that point? It is diverging. Diverging means at any point on the wavefront, the energy is not, it is there throughout the very spherical wavefront, but equally distributed among all periphery of the sphere. And by taking that amount of energy and with respect to distance from that point source, it will reduce. Then how that energy will go and interact with the metal atom to eject out the electron inside the metal surface? It is very difficult because the diversified energy is going with the help of wave theory. But when you think about the particle theory, particle means it is concentrated. Packet of energy is going and interacting with the electron inside the metal, and that is helping to eject out the electron, which is the photoelectric effect. So therefore, the wave nature can never explain the photoelectric effect. And similarly, the refraction, diffraction, interference can never be explained by the particle nature, photon nature. Hence, you cannot tell the light is a wave or a particle, rather it has dual nature. That is the wave particle duality. All the time, the quantum mechanics deals with that in one way or the other. So they are all having this kind of radiations are all having dual nature. Dual means neither particle nor wave, rather all the time it possesses both the nature, that is wave and the particle. And depending on the situation and the phenomena, you have to select which phenomena or which nature of light will help to explain that kind of phenomenon. As I told you, in case of photoelectric effect, it is a particle nature, but in case of diffraction, it is a wave nature. Same X-ray can explain the photoelectric effect, but the same X-ray photon cannot explain the diffraction phenomena. It must be wave phenomena only. Diffraction, to explain, understand the diffraction, you have to consider the wave nature of light. But to understand the photoelectric effect, you have to go for the particle nature of light. Then what that light is? That light is having both the natures. That's why it is dual nature. And the duality is all the time there, everywhere there. But obviously it is linked with the quantum mechanics. It is never classical. All the time it is quantum. Then, yes, that I want to tell. Let us think about the X-ray photon. That photon is having a wavelength of monochromatic radiation 1.54 angstrom or 0.154 nanometer. Right? That is having a definite wavelength because it is monochromatic. So when that X-ray photon is coming and interacting with an atom, right? Let us think about a atom. The monochromatic X-ray photon is coming and interacting with an atom. If you take a material in elementary state, it must consist of a similar kind of atom. So think about one such atom. So then our atom is consisting of a nucleus at the center with positive charge and neutrons, and around the nucleus you are getting the electron cloud. So when the X-ray photon is coming and interacting with the atom, first it will face the electron cloud before going towards nucleus. So now think about only one electron. So what will happen when that X-ray photon is coming and interacting with one electron which is having negative charge? It is a charged particle. Then what will happen by getting that energy from the X-ray photon? It will start oscillating, and whenever any charged particle is oscillating, it will emit the radiations, and it goes with equal probability in all directions. Right? That phenomena is called as scattering. And why I am telling the order length? The wavelength of the X-ray is 1.54 angstrom. Now, all of you might have understand what is the dimension of an atom. Order length of an atom or size of the atom, it is 0.1 nanometer or 1 angstrom. If you think about the nucleus, the order length goes to femtometer, Fermi, 10 to the minus 15 meter. Now think about the electron. Electron order length is extremely small than that of nucleus. Hence, compare the wavelength of the X-ray photon that is coming and interacting with the electron. Obviously, it is very large in comparison to the order length of or the size of an electron. Hence, that is phenomena is called as scattering, because the wavelength order length is extremely large in comparison to the dimension of the object with which it is interacting. And due to interaction, the charge particle oscillates, and whenever any charge particle is oscillating, it will emit the radiation, and that radiation is scattered. And if it is X-ray photon, X-rays will be scattered from the electrons. In that way, when the X-ray photon is interacting with the electron, then it gets scattered. Scattering means it goes out in all possible directions with equal probability. That is scattering. So now think about the material with which it will interact. So hence, atom with which it will interact. There is not a single electron, many electrons are there depending on the nature of the material, may it be sodium, carbon, uranium, whatever it may be. Every element has its own electron cloud, and that will decide how many number of electrons are there and how they're interacting with each other. So then again, when the X-ray photons are coming and interacting with those electrons, every electron is a scattering center for the photons coming and interacting with them. So every electron will scatter the radiations in all possible directions the similar way if you think about a single electron. So what will happen now? All the electrons are radiating the X-ray photons in all possible directions because they are the scattering centers for the X-ray. And now what will happen? Those scattered radiations will superimpose following the superposition principle that you might have learned. So they may superimpose constructively or destructively, depending on the condition of phase or path difference. So if they will superimpose constructively, then the amplitude will go high and hence the intensity goes high. But when they superimpose destructively, then the amplitude or the intensity goes down. So in that way, there are two kinds of superpositions, maybe constructive or destructive. Then by that way, when all the electrons are involved, then those scattered radiations coming from every electron will go and superimpose to give some phenomena lead to constructive interference and some are going for destructive interference. So when it is constructive, means in certain direction you are getting more intensity, whereas in certain direction you are getting less intensity. And in that way, the intensity is distributed when the photon, X-ray photon, is interacted with the atom. Atom means electron cloud, not single electron. So when I will tell the same X-ray photon, when interacted with the electron, the phenomena is scattering. But when the same X-ray photons interacted with the atom, it is no more scattering, rather it is diffraction. There is a difference between scattering and diffraction, right? When you take one single electron, same photon with wavelength 1.5 per angstrom, the dimension or the order length of the wavelength is very large in comparison to the size of the electron, and hence there is scattering, right? But when many electrons are involved there in an atom, every electron will go for that kind of scattering phenomena, and all those scattered radiations are superimposing to give you constructive or destructive interference. So in some direction you are getting more intensity, whereas in some other directions you are getting less. And that leads to the diffraction phenomena, because the diffraction phenomena leads to such kind of energy distribution. Somewhere it is more, somewhere it is less, but it never happens in case of scattering. Once it is scattering, equally distribution in all possible directions. So therefore, when you think about the same X-ray photon or same X-ray photon beam is going and bombarding with an atom, the electron scatters, but the atom diffracts. That is the difference you can understand in terms of order length. What is the difference between scattering and diffraction? So when you think about the grating, what I told in that you might have studied in the +3 level, when such kind of grating is given to you and somebody asks you, tell me how many number of lines are there per unit length in that grating. Very interesting question, but how to judge, how to answer that, how to react with that question? Simply give you a grating and ask, tell me how many number of lines are there per unit length. How to react? Is it with the help of our God-given detector eye, you can count them and tell how many number of lines are there per unit length? No, not at all possible, which is impossible, just impossible, right? And that grating is having a grating element. Every grating is having a grating element, and that order length of the grating element is very important to decide which kind of radiation will help you to design the diffraction experiment, right? And what is the grating element? Width of one line, opaque line, and width of one slit. If width of the line is A, width of the slit is B, then the grating element is A plus B. That is the grating element, and every grating is having a grating element, symbolized as A plus B. If A is the slit width, B the opaque line width, then same thing. or if you take A is the width of the line and B the width of the slit, then also the order length is same, that is A plus B, which is called the grating element. So that grating element is important because you have to compare whether that grating element order length is comparable with the order length of the wavelength of light that you are using to design the diffraction experiment, as you have learned in the laboratories, right? So what happens, you are using the sodium light. Sodium light is actually not monochromatic, it is dichromatic, having two wavelengths, 5890 angstrom and 5896 angstrom. But the instrument or the detector is our eye. Instrument is the prism table having collimator, then the telescope and the other kind of prism table, all those things, they are the instrument. So when you allow the sodium light to go through the collimator, it gives parallel ray, then interacts with the object you are putting on the prism table. Then you are visualizing the light again after diffraction with the grating with the help of a telescope and eye. Eye is also included there. Otherwise, you cannot visualize. You cannot collect the information. Brain cannot know what kind of light is coming with that interaction. So then now, neither the instrument nor the eye is capable of resolving that order length, which is very, very close of 6 angstrom interval. D1 line is 5890 angstrom. D2 line is 5896 angstrom. So the difference in wavelength is only 6 angstrom. So neither the instrument used there nor the eye is having the capacity to resolve these two lines. That's why it is treated to be monochromatic. And mean of these two wavelength is 5893 angstrom. We are taking as monochromatic, but reality is different. That is dichromatic, right? But with that, if you proceed, then what will happen with that light of wavelength that's 5893 angstrom is going and interacting with that element, grating element A plus B, right? So when it is A plus B, the wavelength must be comparable because you are designing the diffraction experiment. So for diffraction experiment, the condition tells that the wavelength order must be comparable with the object about which you want to collect the information. So what is the object in the grating? Object is nothing but your grating element. That is A plus B. Then why I'm telling that? So as I told you that the if somebody will be asked you to tell me how many number of lines are there in this grating for unit length, you cannot count them with the eye or with the visible light available to you. It is very difficult task because generally the students getting that you are using in the UG labs or PG labs are having 15,000 lines per inch. 15,000 lines per inch. That means, imagine what is the length A plus B grating element there is. How can your eye resolve that order length? It is not just possible with the help of visible light, right? So you can never count them. If it is not resolved by your eye, you can never count. And if you are not counting, then what is the solution to that question? How will you tell how many number of lines are there per unit length? Impossible, just impossible. But the diffraction experiment teaches you how diffraction experiment helps you to collect information to answer that question. How many number of lines are there per unit length of that grating, right? How it is, I'm telling, when you are doing the experiment, you are putting the grating on the prism table and light is coming from the collimator, and on the other side there is a telescope with prism table movable. The telescope can be moved to different orders, first order, second order. In that way, you are collecting the information about the theta 1 and theta 2. First order, angle of diffraction, second order, angle of diffraction, theta 1 and theta 2. Others are there, third order, fourth order, many are there. But the intensity is so small that we cannot detect. Our eye cannot detect that intensity. That's why we are maximum going to second order. Because second order intensity is also very, very poor in comparison to first. So, but anyway, by that we are measuring theta 1 and theta 2. So then now what is the diffraction condition here? The diffraction condition is n lambda is equal to A plus B grating element times sine of the angle of diffraction. So if it is for first order n equal to 1 and the angle is theta 1 for first order, then you can write the equation as lambda is equal to A plus B sine theta 1. Similarly, when you are measuring theta 2, that is for second order angle of diffraction, then the same equation will represent 2 lambda is equal to A plus B sine theta 2. because A plus B is common for first order and second order, because you are not changing the order, the getting element, it is same. A plus B is same for both the first order as well as the second order. So when it is first order, the equation is lambda is equal to A plus B sine theta 1. When second order, 2 lambda is equal to A plus B sine theta 2. From both these equations, you can measure what is your A plus B, which is constant for both the orders. Right? So A plus B is equal to lambda by sine theta 1, which is again equal to 2 lambda by sine theta 2. Right? So in that way, you are measuring the value of the A plus B, that is the grating element. So after measuring A plus B, now tell the length of A plus B contain how many lines? The length of A plus B, that is the grating element, contains only one line, because it is one line width plus slit width.
Hello.
Yes?
Excuse me, sir.
Yeah.
Sir, the derivation you are explaining is not visible on our screen, sir.
No, not visible. It is not there at all. I'm just telling.
It is theoretical.
Yeah. No, not theoretical. It is, everybody is doing that in the laboratory.
Yeah, sir. Yeah.
Everybody is doing that if they are doing the diffraction experiment. Right?
Thank you, sir. Please continue.
So it is not there in the slide. I am telling from my side.
Okay, sir.
So that A plus B length is measured indirectly with the help of theta 1 and theta 2 from the diffraction experiment again. So after knowing that length A plus B from that experiment, what it means? A plus B length contain how many lines? Only one. Because A plus B, the grating element, that is nothing but the width of one line plus width of one slit. Hence, A plus B length contain one line. Hence, unit length contain 1 by A plus B lines. Your problem is solved. How many number of lines are there per unit length? So which was impossible, now it is made possible with the help of diffraction phenomena. That is the benefit we are getting with the help of diffraction experiment. For that only people are going to, or students are going to learn that experiment. Grating, diffraction grating, which was not possible to count and tell how many number of lines are there per unit length. It is possible now. How many number of lines are there per unit length? So the problem is solved. So that in that way, diffraction helping us in many ways to collect information which was not possible, but it is made possible with the help of diffraction phenomena, and similarly with the help of scattering phenomena. You see the difference between these two kinds of scattering. One is called a small angle excess scattering, with which I told you at the beginning, my department is well known across the globe at that time. Even now, although the device or the instrument is not with us, but we are taking the help of other devices placed in some other places like IIT's, DRDO, AIMS Delhi, many places they are now having. At that time, my department is the only department in the country who do work with this technique. Only department. Across the country, nowhere, no device was there to work with this technique, what is small angle excess scattering. And we will astonished to know that Professor Krishnamurthy from Jadavpur, Cultivation of Science Jadavpur, actually gave the idea of the small angle excess scattering in 1937. The first person is from India. He gave the idea of small angle excess scattering in the year 1937. But unfortunately, I don't know, he could not succeed to do research in that line. I don't know where is the barrier, but the people across the globe learn the technique and they explore the technique in such a way that nowadays in every 2 or 3 years, there is an international conference on small angle X-ray scattering. But at that time, again, the people and the government of India may not know the advantage of that technique. That's why they have neglected. But the advantage the people across the globe has taken. And ultimately, our department started this research work in 1961. So what is the gap about that 30 years? During that time, people across the globe learned many things, did many research and advanced. And that's why they are developed. We are still developing. There is a difference between developing country and developed country. Right? So in that way, this technique itself starts from our department in the year 1961. Nowhere else was there that kind of device. But now many places, because when the nano world is coming, everybody is interested to go for that kind of technique, because there is no alternative way out to go for learning this nano order length resolution. And it is the best solution to go with the small angle X-ray scattering. So now everybody is going and running after it. And that's why many places like DRDO, Department of Atomic Energy, almost all IITs, very few NITs are having that kind of device now because of this nano only. Because nano order length can never be resolved by any other device so accurately what one can do with the small angle X scattering. So now what is basically means small angle X scattering means scattering at lower angle where the 2 theta value is less than 5 degree. Then what will do that? With that scattering, what kind of information one can collect? That probes the macromolecule. Macromolecule means, suppose for example, you think about cellulose. Cellulose is a macromolecule. Why? Because cellulose formula is C6H12O6 whole bracketed N. N means polymer. If the glucose unit C6H12O6 is the glucose unit, and that unit is when repeated bonded with each other, then it will give you a polymer. That may be natural or artificial. Artificially also glucose is synthesized and cellulose is synthesized, but it is different from natural. I am telling about the natural. So when it is natural, that glucose unit is repeated many a times. That's why it is a polymer. And if it is natural polymer, then it is not less than 10,000 times. So that's why this, imagine the size. That size is beyond molecular size, molecular dimension. That's why it is a big molecule called as macromolecular. And hence that probes the macromolecular structure, like that protein also, same thing in a protein also. That is a macromolecule, big molecule. Then provides non-crystallographic information in nanoscale range order, right? That is a very important application of the small angle X scattering. It provides non-crystallographic information. That's why at nanoorder scale length. But when you go for the other side, that is wide angle X scattering, or in general, it is called as XRD, X-ray diffraction. When that angle goes beyond 5 degree, when 2 theta is more than 5 degree, then we are telling that is wide angle. Wide angle X scattering, or the same thing, one can tell that is the XRD. So here what happens? Here you are detecting not the macromolecules or the molecules, rather you are detecting the atoms, size of the atoms. So provide here the crystallographic information at atomic scale. That is the difference between small angle and wide angle. In small angle, you can go to length order of nano, but with the help of crystallography, XRD, you can never go to that nano order length, rather you are in the atomic length. Atomic length means only 1 angstrom. Nano order is 10 angstrom. So the order length will decide whether you are going for sacs or wax. Wax is the same thing as your XRD. So now crystallography part I will describe a little bit. You see the instrumentation, the principle, how it works is like this. That is powder diffractometer. There is a specimen, then source, slit, then the angle of diffraction, and there is a counter to detect the photons that is coming after diffraction. And the schematic representation of XRD is shown here, that is used for crystallography. So in general, what is X-ray crystallography? Crystallography means first we should understand what is a crystal, how it is different from amorphous. The difference is that the entities, what I mean to say, atoms, ions, molecules, are put in the material whether in an orderly manner or disorderly manner. Like for example, if you think about a glass piece, if somebody will ask you to tell me whether it is crystalline solid or amorphous solid, unless you do and check how the glass molecules are arranged, nobody can tell whether it is crystalline or amorphous. Then how to test? You should have to go for that kind of technique, which is called as XRD. That will tell you the information about arrangement of glass molecules inside glass. And that will tell you whether it is crystalline or amorphous. And it was proved that the arrangement of the glass molecules are not orderly arranged, disorderness. And because of that, we are telling glass is an amorphous solid. Whereas copper is a crystalline solid. How you will know? Copper atoms in copper are arranged in a very regular fashion, very regular order, and hence it is a crystalline solid. So when the entities means may it be atom, ion, molecule. If they are orderly arranged within the material, then you can tell it is a crystalline material, crystalline solid. But when it is disorderly arranged, then it is amorphous. Example of amorphous is your glass. Example of crystalline are many. One such is copper, right? But the very important is the importance is that once you know it is crystalline or amorphous, lot many properties are automatically coming out because crystalline materials are possessing certain properties which are not there with the amorphous solids. So first of all, we should have to identify the material is crystalline solid or amorphous solid. If you know that, most of the properties associated with that material is known, because well-established theory tells that if it is a crystal, it must have the melting point, thermal conductivity, all those things are linked with the crystallographic behavior. So with that, you can know whether it is crystalline solid. If then all such properties are associated with that material. But it is not complete characterization. It is a first. So that is the reason why people nowadays think that XRD is the signature to characterize a material. Signature means unless you know, you can never tell about any properties. First of all, everybody is going after that. That is, whatever material it may be, may it be living or non-living, first you have to go for XRD, because that will tell you the rough idea you will get out of that experiment, whether it is crystalline solid or amorphous. Like for example, why I'm telling non-living, because that there is a very new branch evolved nowadays, which is called a protein crystallography. Same thing, protein crystallography, whether it is orderly arrangement or disorderly arrangement, same crystallography, right? So those informations are, because unless you understand the crystallographic behavior of the protein, you can never understand how that protein will active, how that protein will act, how that protein is having its properties. Because the body is consisting of various kinds of protein, but which all proteins are meant for different kinds of functions inside our body. So to understand the function, you should have to understand the structure, and the protein crystallography is one of the most important branch evolved across the globe. Many people are working over it to know the structure, because unless they understand the structure, they can never go for the function. Every protein has different function, and unless you understand the structure, you can never explain what is the function of that kind of protein. So in that way, that is different thing. But I am telling what, yes, crystallography means if you take the material, do the experiment with XRD, it will tell you whether it is crystalline solid or amorphous solid. First part is over. That's why it is a signature, right? Then after doing that, knowing even it is crystalline solid or amorphous solid, but again, the material that I am telling is broadly classified into three categories, not two: amorphous, crystalline, semi-crystalline. All polymers and all polymeric composites are semi-crystalline. Semi-crystalline means partly crystalline, partly amorphous. And it has a very complex property. That's why, because it is combination of two phases. Crystalline phase is there, amorphous phase is there, and along with that, voids are present. You understand the structure, how difficult or how complex the structure is. All polymers and polymeric composites, may it be natural or artificial, are belonging to that category, which is semi-crystalline material. So therefore, to characterize a polymer is a difficult task in comparison to the metals that we are getting, like for example, copper. Simply you go for the XRD, you will get everything. But when you are going to characterize a polymer, it is very difficult, because there is crystalline region. What kind of crystal structure is there? In that region, you have to identify. Again, amorphous region, and the voids, they are present generally in the amorphous region. If you understand all those things, then only you can understand the polymer structure. And unless you understand the structure, there is no way to characterize the material. Characterization means structure property relation. Understand the structure and then explain in terms of that structure the properties. That is called as characterization. So therefore, when you are telling crystallography, crystallography means knowing the geometrical form of the material or the crystal and its relevant properties is called as crystallography. You have to understand the geometrical structure, and then relevant properties associated with that crystal structure is coming under that branch, which you call as the crystallography. So to know all those things, we are needing some probes. Probes means radiations, like X-ray is one such. That's why the branches are evolved. If you are using X-ray, the probe, then it is called as X-ray crystallography. If you are using electron beam, then it is electron crystallography. If you are using neutron, then it is neutron crystallography. Like that, it is named, whether it is X-ray crystallography, neutron crystallography, electron crystallography, because of the probes, whether it is X-ray, electron, neutron, right? But all are collecting the similar kind of information. And the only difference in neutron and X-ray is that X-ray is a neutral particle, whereas neutron is having some magnetic movement. So if the material is magnetic, then better to go for the neutron crystallography, neutron diffraction, neutron scattering experiments. But the problem is that our country is not now having only one source for all community to do research work in that field, is at Dhruva Reactor, Bar, Mumbai. There is a long queue. if you are going to do such experiment, either neutron diffraction or because for a diffraction experiment, it needs high flux, and high flux source is only the Dhruva reactor at Bark, Mumbai. And people are doing, because what to do? There is no alternative way out. You cannot use the low source, because low source means flux is low. The information collection may not be good. So you have to wait for a long time. Like for example, synchrotron radiation, which is only source there in our ice. What is that called as Indore? At Indore, it is there. It is under Department of Atomic Energy. Synchrotron radiation means all kind of wavelengths are produced at a time. You can select all the wavelengths relevant to what order length information you need. That's why it is synchronized. You can design your experiment depending on order length, what you want, what order length information you want, and select your wavelength. And that is the only source available in our country is at Indore. I forgot the name exactly. That is under DAE, Department of Atomic Energy. And people are waiting and going and doing their experiment to understand the structure and material characterization part. They are doing there with the help of that synchrotron radiation in our country. But usually people, when it was not there, people go abroad and to do the experiments to understand the structures. So whether it is X-ray crystallography or neutron crystallography, it depends what kind of material you are dealing. If it is magnetic material, better to go for neutron crystallography. But if it is non-magnetic, better to go for X-ray crystallography, because X-ray sources are plenty, laboratory sources, but neutron source is very difficult task. Unless there is reactor, you can never get the neutrons. That's why you have to wait for a long queue if you are interested to go for neutron crystallography. So like that, the PICS tells what kind of crystal structure it is, whether it is cubical or trigonal, tetragonal, many. 7 systems of crystals. All those systems can be resolved by XRD, knowing the peak position and peak planes. That will tell you what kind of crystal structure you have, may it be cubic, tetragonal, or many. All 7 systems are resolved with the help of this XRD only. Yes, the information in a diffraction pattern. I told you about the XRD, X-ray diffraction, or phase identification. Phase means it is the chemical composition of the material. Chemical composition, for example, if you tell glucose, chemical composition is of carbon 6, hydrogen 12, oxygen 6. That is the phase in cellulose. And similarly, crystal size, what is the size of the crystal? What is the crystal quality? What is the texture? Texture means orientation, how they are oriented within this material, and crystal structure. Ultimately, you are getting the crystal structure with the help of that diffraction pattern, that is XRD. Similarly, thin film samples can also be done with the help of XRD. It goes like this: coating, substrate, then goes X-ray, interact with the film, then the smaller volume, that is the less intensity scattered beams from the film. Obviously, because the material number of atoms involved there in the film is less in comparison to bulk. Then the grazing angle incidence means at a small angle from 1 to 5 degree. If it is there, then you can do many things to collect the information about that thin film. That is called as grazing incidence, GI-SEX, grazing incidence, small angle X-ray scattering. Grazing angle usually only polycrystalline sample. I told you the polycrystalline means various crystal systems are there in it. That's why it is poly, more than one crystalline structures are there. So to resolve that kind of structures, you need this grazing incidence, small angle X-ray scattering at small angle. And this is semi-crystalline material. I told about the polymers. Polymers are all having both crystalline as well as amorphous phase. The peaks correspond to crystalline phases, and the rest part is the amorphous. And from there, you can identify what is the Segal's formula to tell crystallographic index, and the Serres formula will tell you the crystallographic size. And all the symbols are used written in the side, right? Crystalline size is CS, K is the Serres constant, lambda is the wavelength of X-ray, beta is the full width half maxima, and peak position is theta. And similarly, I002 means intensity corresponding to that peak with a plane 002, and I amorphous is meant for amorphous intensity peak. That is not a peak, it is rather valley. Similarly, I told you about the amorphous material. You look the difference between crystalline and amorphous and semi-crystalline. That was polymer was semi-crystalline. Now it is amorphous like glass, right? Then next comes the small angle X-ray scattering. It is non-destructive. The most advantage with small angle X-ray scattering is that in case of XRD, one has to go for powder samples. But if the sample is liquid or gel, no way to go with XRD. How to resolve the issue? But in a small angle X-ray scattering, any, may it be gel, may it be liquid, may it be gas, may it be solid, all are possible. That's why it is most advantageous technique to characterize the material at nanoscale order length. This technique is the key tool to determine the structural information of macromolecules based on the contrast, but the contrast here is the electron density, right? Unless there is electron density difference, you can never get the small angle X-ray scattering. So the contrast means, like for example, I will write in blackboard on a black pen, there is no contrast. But I will write on a chalk with white chalk, then there is a good contrast. That is the contrast. So similarly, in the meaning of contrast here for small angle X-ray scattering is the electron density. There should be two phases with different electron densities to have good intensity of small angle X-ray scattering. But in case of neutron scattering, the contrast is not electrons, rather it is called the nuclear mass, nuclear number, that will decide the contrast for neutron scattering or neutron diffraction experiment. And similarly, if it is light scattering, light means monochromatic laser, light scattering, then the contrast is the refractive index. So depends what kind of scattering or diffraction experiment you are designing, whether it is X-ray or it is neutron or it is light. But for X-ray, electron density is the contrast. There should be a electron density difference between the two phases. Then characterize the structural information in macromolecular dimension. Dimension goes like colloidal. Same thing is colloidal dimension. Up to 100 nanometer is colloidal, or that is 1000 angstrom. So 1 to 100 nanometer length order is, if there in the material, you can tell that material is a nanomaterial. May it be in 1 dimension, may it be in 2 dimension, may it be in 3 dimension, but at least 1. Then only you can tell that material is a nanomaterial. Then collect information in small angular regions. Then forward the information for statistical averaging over the larger dimension samples. So in that way, again, I'm telling people are going to do this similar kind of work with electron microscopy, TEM. Only the difference is that when you go for any electron microscopy will enlarge the size to understand the structure. That part is correct. But at the same time, when you are going for calculating the size of the grains, crystallites, everything, you have to go for averaging. Averaging means, suppose, for example, you are doing with small SEM or TEM, then what happened there? A beam of electron is coming and interacting with the sample. So whatever image is coming after interaction is corresponding to that particular spot to which the electron beam is bombarded. But what about the rest part? And with that one spot, how can you tell the material is consisting of this structure or these grains, these crystallites? It is just not possible unless you scan the whole sample by the electron beam maximum times, and time is not permitting you to go for repeatedly for 100 times. Unless you do it for 100 places, the averaging dimension that is evaluated from electron microscopy, may it be SEM or TEM, is never acceptable in research level. Never. It's never acceptable in research level. It may have the rough idea only, because the statistical averaging with only one image at one spot of the sample may be giving you wrong information about the grain size, crystallite size, for what you are doing the experiment in electron microscopy, right? So that, but in case of this X-ray scattering, what happens? If you take the sample, irradiate the sample with the X-ray beam, the whole sample is exposed. So whatever information that you are collecting in terms of intensity is much more better about the structure so far as statistical averaging is concerned, and which is very much essential for research work, very much essential for the research work. Research work need that kind of accuracy, which is never done with the help of electron microscope. May it be scanning or may it be transmission. But why the people are running after SEM and TM? Because the reason is very clear. People all the time tries to go with an easy way. And it's the most easiest way, because directly one can visualize what is there inside, but they don't know how much accurately they are collecting the information. That is the requirement for research. The requirement of research is how much accurately you are evaluating the structure. So electron microscope is easy because directly you can visualize and tell what kind of grain, what kind of crystals, what kind of other voids, empty spaces, whatever it may be. Directly you will visualize because it is an image. But in case of scattering or diffraction, it is very difficult task unless you understand and expertise in that field. Collecting information is not that easy task. That's why people are afraid of scattering and diffraction techniques. It is the only reason. But one must have to understand, if somebody is going to do research work, the most important job he or she want to learn is that how accurately I will calculate, how accurately I will collect the information. If they are not doing that, then they are not doing research. So in that way, the small angle access scattering is very much important so far as the statistical averaging dimension of the structure are concerned, may it be in crystalline, amorphous, polymer, polymer composite at nano order length. Is the best technique to resolve that order length in any kind of material, may it be in solids, liquids, gases, whatever it may be. This is, yes, you see, when you scan your sample, it has three parts. First part is Guinean region. It is clearly mentioned. The scattering vector means Q is equal to 4 pi sin theta divided by lambda. It is inverse of length. So that's why it is in reciprocal. You see, why the difficult task is with scattering and diffraction, because you are collecting the information in terms of intensity, and intensity collection is not in real space, rather in the reciprocal space. And that's why the scattering vector is in reciprocal space. With this Q is 4 pi sin theta divided by lambda. Lambda is the length. Length inverse is the dimension of Q, hence in reciprocal space. So whatever informations are there in intensity is never directly be measurable. It is indirectly measurable because you are in a Fourier space. Scattering intensity is going to Fourier space. Informations are there in the intensity, but again you have to come back to the real space by Fourier inverse transformation. It's a mathematical process. If you do that, then you can collect, and people are collecting. But see how important it is, because this scattering curve is having three different regions with different Q values. First region is with some Q value, which is called the Guinean region. The second is having some Q value, which is called the Fourier region. And the last region is the Porot region. And beyond that region, it is going to wide angle. That is XRD, right? So now what these regions, three regions are basically meant for. The Guinean region is responsible to tell you about the size. The Fourier region is responsible to tell about the shape. The Porot region is responsible to tell you about the interface. So all three informations at a stretch, at a time, with good statistical averaging, one can do with small angle X-ray scattering, which can never be done by any other technique. Never be done. Thus, that is a concluding remark. It may now be calculated that X-ray optics concluded. The X-ray optics can do a lot of research for characterizing the materials both in living and non-living, using different techniques like scattering, diffraction, spectroscopy, absorption. I hope I can stop it here. Thank you all for patience listening.
Thank you very much, sir. It was very informative lecture, and I hope so. Students also received some more important information. Now, I would like to request all the students, please, if you have any kind of doubt, any kind of question, then you are most welcome to share their views and questions. Dr. will address you regarding your queries.
Yes, yes, you are most welcome. Questions are most welcome.
Madam Sahu. Please ask the student.
Because unless the questions are coming, I think that they will not understand the things, what I told. It is useless for me. Questions should come. Archana, any queries from the student side or your colleague side?
Hello.
Yeah.
Sir, here some disturbance is there. I'm continuing here.
Okay.
Sir,
Man, just question answer. Mas, Archana, apun na? Okay.
Sorry, sir. Due to interruption of electricity,
Ah,
we
okay.
were
Okay.
disconnected.
No problem. No problem.
Yes, Madam Sahu. Any students having any kind of query?
yes, sir. Sir, here are the students, sir. I want to ask some question. Any question?
Yeah. Most welcome, Archana.
No, sir. Actually, the lecture was so helpful and so interesting, sir.
But still, there should be some questions, queries from student side, at least. Yes. Someone is raising hand. Please.
Good morning, sir.
Good morning.
Sir, I'm Jayashree from NIT Raipur. Sir,
NIT Raipur. Okay.
yes, sir. I am working under the supervision of Dr. Sadhna Agrawal, ma'am.
Yeah, I know you. Know you. I met you once in Raipur itself, NIT
Yes,
Raipur, right?
yes, sir, I remember it.
Yeah. Tell.
So, sir, I have just a question, sir. At first, I would like to thank that you clearly, in a very good way, elaborately describe all the things. So it is very helpful to
But the
me.
time is short. Actually, the time is short.
Sir, I just want to know. So, without going to SAM and TAM, can you calculate grain size from small angle X-ray scattering?
Not particle size.
We can calculate particle size.
Yeah,
But
particle
for
is
a
grain.
powder X-ray XRD, we can
Yes.
just calculate
Powder.
the triplet size.
Same
But
thing.
in this case, we can calculate the particle size, which we go through TAM in case of XRD. Na?
Yeah. I told you the difference between electron microscopy and scattering and diffraction.
Okay, sir. Thank you.
People are doing across the country, across the world, without understanding what they are doing.
Okay, sir. Thank you.
Yes, Madam Sahuji.
Yes, any more question from any participants? Sir, let me, I take my privilege to introduce my department if you give me permission.
Sure. No, what permission? I should learn. I should.
Sir, here our department, including our principal, sir, we have 15 faculty members. And here in our department, including research work, our faculty do very hard works to achieve the results in national level examinations like JAM, NET. And here we have 80 student intakes in MSc classes and 40 student intake in honors classes and 340 students intake in BSc pass courses. And sir, well, I have joined this department from 2014 and under here from 2014 onwards, near about 700 plus students are pass out as MSc courses, and more than 500 students are pass out from honors courses. And I think more than 1,000 students have got their BSc degree from this department as as physics as one of the main subject. And sir, I wants to introduce our colleagues to you too. Sir.
Yeah.
Sir, here. Sir, I will introduce Dr. JK sir, Dr. Jitendra Kumar, and he is specialist in nanomaterials.
Oh, good.
Sir, here, Sombir sir, Mr. Sombir, and she is a JAM and NET specialist. Sorry, sir, he is. And let me introduce Poonam ma'am, and she is specialist in NET and JAM classes. Sir, he is Manjit sir, and she is specialist in all in our lab. We have 5 labs in